like you said, my capstone is on the response of the ear to over-the-ear headphones. So the goals of my project were to create a system which measures the ear response to over-the-ear headphones, as well as obtain the response of a series of different model ears. The purpose for this project is to develop a better target for equalizing over-the-ear headphones, because understanding how the outer ear responds to sound from over-the-ear headphones is the first step in creating a target response curve to apply to headphone frequency response. So what's frequency response? Well, it's how a device responds to a wide range of frequencies, with here with the amplitude being the intensity of the sound measured in decibels, and the frequency being measured in hertz. And this is a little example would be, maybe this is a nice flat signal from a speaker, and maybe this is what your ear hears. But that's not. This is just a simple example. Okay, so decibels. Decibels are measured on a logarithmic scale, meaning that sound with maybe 50 decibels is 10 times as intense as sound at 40 decibels. So every time you go up, the intensity increases by a factor of 10. The intensity of the sound is not to be mistaken with the loudness. The perceived loudness of sound actually, it roughly doubles for every 10 decibels you go up. So, like a normal conversation at 60 decibels, you move that up, and a vacuum cleaner is about twice as loud as that. But the intensity is 10 times as intense. It's a little confusing. Here we have a nice little diagram to help you understand maybe like the frequencies of different kinds of instruments, maybe to give you a better understanding of like what range of frequencies I'm going to be talking about. So, violin or piccolo is kind of a high frequency instrument with a nice bright sound, whereas like bass is a very low frequency kind of instrument. So there's a little introduction to frequency for you. Okay, so my project is focusing on the outer ear, which is the pinna and the canal, as well as the eardrum. And the pinna does a great job of localizing sound with these, sorry, my hand's a little shaky, with these ridges and depressions in the ear. So, and those ridges and depressions act as weak reflectors and resonators for sound waves. And these ridges are unique to every individual, as well as individual for your ear. So your left ear is actually different from your right ear, and that can next slide. Okay, here is a breakdown of the different parts of the ear, as well as the head and the torso, which affect the way that you hear the sound. So here you can see one is the head. The head actually has its own response, as well as the torso seen here, number 2. And the pinna, which I was talking about, the pinna flange right here is number 4. So it's a nice little green curve you can see right there. And there's the concha curve, which is right here, and the ear canal curve. Okay, so sound okay, hold on. Okay, so not only does the shape of the ear and the head and the torso affect the way that you hear sound, but the direction that the sound's coming from, or your position relative to where the sound is, where the source sound is, it affects your hearing. So sound that's coming up at you sounds different than sound that's coming down at you, just like how sound coming from behind you sounds different than the same sound coming in front of you, due to like your positioning of your ears, etc. So here's the azimuthal dependence, meaning the in-plane angle. As you can see, around 6 kilohertz, there's almost a 10 decibel difference between sound coming 45-degree angle and sound coming at 135 degrees, which is 180 degrees difference. So the 45 is coming at a 45 in front of you, and the 135 is coming behind you. And since there's a 10 decibel, is it 10 decibel? Looks like it's, yeah, 10 decibels. It's going to be twice as loud. The sound coming at you, in front of you, is twice as loud as the sound coming behind you. So there's obviously the Azimuthal Dependen has a lot to do with how you perceive sound. And not only is it in the azimuthal plane, but it's sound coming at you from up or down. And you can see here at about 6 kilohertz, there's about a 20 decibel difference, meaning that the sound coming down to you at that frequency is going to be 4 times as loud as the sound coming up to you at that frequency. So the elevation of the sound has a lot to do with how you perceive, how you hear. Okay, so we need to go into a little bit of the history of standardizing or equalizing headphones. So in the 70s, they used free field equalization to standard high fidelity headphones. And free field equalization is basically, it tries to mimic the experience of sound coming directly at you at the same elevation of your ears, but none of the sound gets reflected. It's an anechoic room, so you're only getting the sound from the source. But that sounded kind of a little bit dry, so in 1984, Gunther Tyler suggested that diffuse field equalization would be a better way to equalize headphones. And it did a good job of eliminating some of the timbre falsifications that the free field had. So like maybe your listening experience was a little boomy, maybe this will fix it a little bit. And the diffuse field equalization is as if you're listening, it's as if all the sound is coming to you equally from all angles. And it's all being reflected equally at all angles as well. Which for headphones is kind of what you're experiencing anyways, because it's just 2 big speakers right in your ear. But this guy, Dr. Sean Olive, suggested that headphones instead be equalized to that of a standard living room to give you a more natural listening experience. Because, you know, having sound coming at you from all different angles, or from all angles, and being reflected all equally, it just isn't a natural listening experience. So Olive decided to use this standard living room as his equalization, which is kind of like free field, except some of the sound is going to be reflected off of the walls, like the ceiling and the floor. So going into what I want to do is I want to try and make the listening experience a little more appropriate. So, you know, it's not like you're listening to a concert in your living room. You know, that doesn't sound natural, or that just doesn't happen. You listen to live music in maybe like a concert hall. So on campus we have one of the best concert halls, Wow Hall. And I want to equalize these headphones to Wow Hall. Here is a nice graph of the early decay time as a function of frequency. And basically what the early decay time is a measure of is the ability of the hall to reflect the sound. And as you can see here, we have a nice kind of flat response from the wheel hall. And the flatness is good because it means you're not going to get any kind of like, not one specific frequency is favored over any of the other ones. So you're not going to hear like some boominess or some edginess in the music because the hall has a good ring. It flattens out this. It supports all frequencies equally. And the other nice thing about this curve is, or not so much of a curve, it's like a straight line almost, but the nice thing about it is that it reflects just enough and not too much, not too little. which makes it a great kind of room to standardize our headphones to. Okay, so we need to go into this whole standard ear thing. It was defined by the International Electrotechnical Commission in 1990, and it allows manufacturers to standardize the acoustic performance of their headphones or cell phones or whatever. But the problem with this thing is that it's the agreed standard. So it's not the average ear by any means. It's just, hey, let's just say this is the ear. This is the ear we're going to standardize everything to. And I just think that's ridiculous. So I speculate that the standard ear doesn't do a good job of standardizing the frequency response of a real person's outer ear. There's just too much variation in the size, the length, the depth of some of these cavities here, like the concha. Like look at that. It's so dark. It's so depth, as opposed to like this guy's right here. You can see into it. Yeah. So there's a lot of variation, and that's my reasoning for thinking the standard ear is ridiculous. Okay, so I needed to use 3D printing in order to get these ears because I had no other good way of figuring that out. And so I printed about nine ears, and they're all relatively different, closely modeled to or actually scanned off of a real person's head. And I also modeled an ear canal with average value for length and width, and so the average values were like 25 millimeters long and 7 millimeters wide. And I use this great online 3D modeling software on Tinkercad. Okay, so here's the images. Here, this is the canal I made in Tinkercad. And as you can see, this chunk right here, that's supposed to like plug into our microphone down here. I'll go into that in a second. But the effective length of this canal is roughly 25 millimeters, like I said. And you're gonna think that this looks kind of weird, but if you add up all of these little discs and you average them, the average width is roughly 7 millimeters, like a normal ear canal. Okay, and this is, so now that I have the ears and the ear canal, I needed something to kind of act as the head of my system. And so I made this nice little box. Unfortunately, the ear canal is kind of, or the eardrum rests in your ear at an angle, so building this wasn't really easy, but I got it done. And here's a nice image of the ear on our artificial head. And you can't really see the microphone, but this image over here will help out. So basically this is the setup. I have my ear right here, acting as the ear, and here's the canal, and then the microphone is acting as the eardrum. And here's my setup. So I had the headphones resting rather tightly over the ear, I guess, but you gotta do what you gotta do. You can't really see the canal is there. It's in black. I made it with black filament, so you can't see it in this image, but there's the microphone. And these are all connected up to my computer. And the way that I got the response of the system is by sending pink noise from the microphones through the system. And pink noise is pretty cool because it has equal energy for equal energy for proportional bandwidth. So that means the energy from 40 hertz to 60 hertz is the same as 4,000 to 6,000 hertz. So you get it has a nice flat response. Okay, and so here's some of the amazing data I collected. It includes all 9 ears in the system, and then I also collected just the canal. But there's a couple more things I need to do in order to really finish this part of the project, but we're at the end of the show, so hopefully somebody will take over for me. So things that need to get done, I need to obtain a response of just the microphone with the headphones. This is important because I wanted just the frequency response of the ear. And so right now I have the frequency response right here, this data is actually the summation of the canal, the microphone, or the canal, the headphones, and the ear. So I have the canal, I can subtract that from all of the ears, but I still have the headphone response mixed into the data. So I need to, or somebody else needs to, modify my artificial head and get the response of just the headphones. And then after that, measure the frequency response of each of the ears in while Hall. And then knowing both of those frequencies responses, we will finally be able to determine target equalization for headphones, for over the ear. And I just want to thank Dr. Jones for being so patient with me, had to teach me a lot about acoustics. I want to thank Dr. Pauls for giving me access to this awesome printer, which I did print some stuff that I wanted to print myself, not just the ears. And I want to thank the whole, and I want to thank the whole department because, yeah, you guys really pushed me to do something I didn't want to do today.